Hello everyone. This video going to show you another example for a moment of inertial calculation. And this moment of inertial calculation, this is kind of different than the previous example because in this example you have to calculate so-called neutral axis first. Okay, and I think you need some different demonstration of this. And previous example, we calculate this moment of inertia of this composite area, and this problem already tell you okay which axis. Okay, you calculate moment of inertia on the base of the told axis. Okay, simply speaking, the problem tell you which axis you are going to calculate. The moment of inertia. Okay, but okay, in this example, especially in beam calculation, stress calculation in the beam, you need to calculate the neutral axis before you calculate moment of inertia. Okay, because in bending moment, in the beam stress calculation, the bending is based on there's a axis in which which is the reference axis of the bending. Okay, and you need to calculate this first. Okay, and the calculation of the neutral axis is very similar to what you did in the centroid calculation before. Okay, very similar. Okay, so let's look at this problem. It said this is a beam. Okay, and this is a cross section area of a beam. Okay, it's calculate the problem want to calculate moment of inertia. Okay, and with respect to its neutral axis, and neutral axis it doesn't tell you where is the neutral axis. Okay, so the neutral axis. Okay, so we consider the horizontal neutral axis because. But why? Because in most case, because suppose there is a beam here, is a cross section area. Most of the time, external loading is here. External loading is here. Okay, external loading is here. So the beam start to bending. Okay, and it's bending with the bending, and its bending will look like okay. Maybe this is the graph. You push a force here, it start to bending. Okay, and here is your neutral axis. Okay, so we consider horizontal neutral axis. We don't consider the vertical neutral axis. Okay. So for the horizontal neutral axis. Okay, so where is the so like I say, where is the neutral axis in the y direction? Okay, so in this problem, so we need to use the technique we used before, just like we calculate the centroid composite area. So did you calculate the centroid composite area? Yeah, the first step, the first step is the same. The first step is dividing your composite area into your simple simple area. Okay, so for this shape, so this cross section area, I can decompose or divide this shape like this. I divided the shape like this. Okay, and call this 1. I call this 2. Okay, I call this 3. Okay, so and then determine the centroid of each part. Maybe it's too big. Okay, then determine the centroid of each part. Where should be? Okay, I call this 2. I call this 1. And determine the centroid of each part first. Okay, first, and this shape. And you look at these three shapes. Okay, it's all rectangular, so it's very easy to determine the centroid. Okay, the centroid probably this is or not probably it must be here. It must be here, and is the centroid. Maybe I think Yeah, it's hard to. Oh, maybe it's here. Okay. So what's the centroid of this area in y direction? So it will be the denominator is a1 plus a2 plus a3. This area of each simple shape. So and this is a1 y1 plus a2 y2 plus a3 y3. Okay, so what's our A1? Okay, what's our A1? Okay, so this is 0.2 and here is 0.1, and this shape, yeah, it must be symmetric. So this must be 0.05. Okay, here must also be 0.05. Okay, so what's our A1 and A2? A1 and A2, you see from the graph, it's the same. Okay, A1 and A2 equal to 0.1 times 0.05. So equal to 0.005. Okay, so what's our A3? A3 is the middle part. Okay, it's the middle part. So this here is 0.1. And the height is 0.3 plus 0.1. So it's equal to 0.1 times 0.3 plus 0.1. So it will be 0.04, right? 0.04. Let me check. Yeah, let me check again. 0.04. Okay, so that's the area 3. Okay, so what's our y1? Okay, the centroid of the first area and in the y direction. So here is the centroid, here is 0.1. So let's set our base. Okay, I set this base, our base here is 0. So here is y1. What is y1? Okay, here is 0.1, so it's centroid, so y1 must be 0.05. So the same thing happened on y2. Y2 also 0.05. Okay, so what's our y3? Y3, okay, the height is 0.4. The centroid must be 0.2. Okay, centroid of rectangular shape must be easy, right? So you can put all the information in there. So it's 0.005 plus 0.005 plus 0.04. So this is 0.005 times 0.05 plus 0.005 times 0.05 plus 0.04 times 0.2. Okay. So, and then use your calculator. I think it must be equal to, I just tell you the answer quickly. So check by yourself. Okay, it's 8.5 times 10 to the power minus 3 and divided by 0.05. So it's about 0.17 and units meter. So, okay, so the centroid probably here, and its distance from the base is about 0.17. Okay, here is 0.17 meter. Okay, so that's centroid, neutral axis of this composite area. Okay, and then we have to calculate the moment of inertia with respect to this neutral axis. Okay, so that's the second part of this problem. Okay, this is the first part. Okay, this is the first part. Okay, so okay, so where should I divide it? Oh, sorry, erase. Okay, so maybe I just erase here. Okay. Sorry, sorry, I drew the wrong. Okay. So I drew the wrong picture. Okay, so I just made a modification. Okay, so it's here is neutral axis. So sorry. So the centroid is here, I think. It's very bad at drawing. So centroid is here. Okay, centroid is here. So here is neutral axis. Okay, so it's 0. It's 0.17. Okay, this is a centroid, and this is centroid. centroid of 3. Okay, that's the correct picture. Okay. So we also divided. Yeah, we use the same division 1, 2, 3. Okay, no change. So we start to calculate the I1 first. Okay. So right now you have to be careful. Right now your neutral axis is here. Here is your neutral axis. Here is your neutral axis. You have to calculate the moment of inertia with respect to this neutral axis. So for I1 and I2, you see right now the rotational axis, so-called neutral axis, doesn't pass through their centroid. The neutral axis right now does not pass through the centroid of 1 and 2. So you need to use the parallel axial theorem to calculate the moment of inertia of 1 and 2. Okay, so first of all, before use the parallel axial theorem, you still need to use the formula for the moment of inertia formula for the rectangular rotating around its centroidal axis. So it's 1/12, and the height b times height cubic. So what is your b? So be careful. Right now, this is the neutral axis. Right now, here is your rotational axis. So here is your b. Right now, the b is here. Right now, the b is here, and h is here. Be careful. B times h cubic. Right now, your rotational axis is here, so your b is here. Okay, then this is your height. So okay, so what is your b? It's 0.05. It's 0.05, and your height is 0.1 meters. So it's 0.1 cubic. Okay, so what's the value of this? Let me see. Did I calculate it right? Sorry. No. Oh, sorry. Not even me make a mistake. Okay, we have to use parallel axial theory, and we have to plus area and times the d square. Okay, so the area of this area of 1 and area of 1 is 0.05 times 0.1. 0.05 times 0.1. This is your a, and you have d squared. What is your d? D is the distance between your centroid and the rotational axis. So be careful. What is your d? Okay, right now your d for area 1, your d is here. Be careful, your d is here. Your d is here. Your d is here. So what's the distance here? Okay, so this is 0.17, right? So here is 0.05. So here is 0.12. Got it? Here is 0.17. Okay, and here is 0.05. So here is 0.12. Got it? 0.12 and square, right? AD square. Okay. Yep. Okay. Be careful. And then use your calculator. I think I1 equal to I2 is. I think my calculator is 7.617 times 10 to the power minus 5. So this is the. Let me check the answer. I have to double check the answer. 0.13. And times 0.05 divided by 12, and plus 0.12 times 0.12 times 0.05 times 0.1. Yeah, it's 7.617 times 0.5. 10 to the power minus 5, and the unit is meter to the power 4. Okay, so that's I1 and Y2. So finally, what's our I3? Okay, I3 maybe I erase here. Okay, so I3, I3 is the same thing. Right now, the neutral axis does not pass through the centroid of 3. Okay. Okay, you see from the figure, it's very clear. It's very clear. Your centroid is here, your neutral axis is here. So right now, your neutral axis does not pass through the centroid. So you also have to use the parallel x theorem to calculate the moment of inertia of 3 with respect to this neutral axis. So I3, okay, so first of all, we still need to use the moment of inertia rotating around the centroidal axis. So yeah, okay, so right now neutral axis is here. Okay, here, so here is your B. Again, here is your B. Okay, here is the rotation axis here. So here is your B, and here is your H. So B H cubic, don't forget. So your B is 0.5 and H is 0.4 cubic. Okay, that's for centroidal axis. You plus AD square. AD square. Okay, A is 0.1 times 0.4. 0.1 times 0.4. And what is your D? Okay, right now your D is distance between your neutral axis and the centroid. Here is your D. So what is D here? Okay, so what's the distance here? Okay, here is 0.17, and this is the centroid of the middle part. So the Y, so here must be 0.2. Okay, maybe not very straight. Here must be 0.2. Okay, here is 0.2. Okay, and the Y bar, the centroid is 0.17 is here. And now the centroid of the neutral axis, the Y neutral axis is 0.17 meter higher than the base. And now this, because this is a centroid of 3, and the height of the centroid of 3 is 0.2 based on this coordinate. So here, the small distance here is 0.03. So be careful. So this is 0.03. And this is your AD square. Okay, so you'll have I3. Okay, I3, let me check the, okay, let me check the answer. Okay, 0.1 times 0.4, 0.4 times 0.4 divided by 12, and plus 0.1 times 0.4 times 0.03 times 0.03. Okay, so the answer is 5.693 times 10 to the power minus 4. Okay, so what's the total moment of inertia with respect to the neutral axis? So we just I1 plus I2 plus I3. So I1 I2 is the same, so it's 2 times I1 and plus I3. So I think that will be your final answer, 0.722 times 10 to the power minus 3 and meter to the power 4, meter power 4. So let me check. 2 times 7.617 times 10 to the power minus 5 plus 5.693 times 10 to the power minus 4. So it's 7. Yeah, the correct answer is 7.2164 10 times to 10 to the power minus 4. But I think it's the same answer from the textbook, the same as textbook. So in this problem, okay, we calculate moment of inertia, but this problem just doesn't tell you where the neutral axis at the beginning. Okay, and this is a more common situation. Okay, especially in beam calculation, especially stress in beam. Okay, you need to calculate neutral axis first. Okay, and the calculation of neutral axis is very similar to what you did in the calculation of the centroid of composite area. So the strategy is divided your composite area into a simple shape, and then determine the centroid of each simple shape, and then use the formula to calculate the moment of neutral axis of the composite area. And after you set the neutral set the neutral axis, and then you can calculate the moment of inertia with respect to the neutral axis. And most of the time, the neutral axis does not pass through the centroid of each part. Like this example, the neutral axis is here, and the centroid of the three area is here, here, and here. And you see the neutral axis, the axis does not pass through the centroid of each part. So in that situation, you need to use so-called parallel X theorem to calculate the moment of inertia of each area and then add them together to get your moment of inertia. Okay, and this is very important in the stress calculation in beam, and I hope you can understand the process. Okay, just start the video here. See you in another video. Bye bye. Okay.